Welcome to the virtual booth for our 2018 open project on high power density compact drive integrated motor for electric transportation, being led by the Georgia Institute of Technology. Our project focuses on achieving more than 3 times increase in power and torque densities in traction motors by a combination of embedded microfluidic two-phase thermal management, new silicon carbide-based drive topologies, and integrated power electronics packaging. Our thermal management approach uses micropillar array-assisted coolant delivery into stator slots for reduced thermal resistance. The soft switching approach for the drive topologies results in significant improvement in efficiency, and by fundamental advances in silicon carbide packaging, we plan to achieve a compact integration of the drive and the motor. Our goal is to facilitate the US leadership in electrified ground transport and more electric aircraft markets. Our project involves 6 key activities. The numerical modeling activities in support of multiphysics design involve electrical, electromagnetic, thermal, thermomechanical, and fluid flow simulations. The thermal management efforts involve implementation of our unique embedded cooling approach in laboratory scale experiments and further improvements to it through parametric explorations. Testbed implementations of the approach performed in partnership with vendor MTT Technical Services will show the scale-up of our approach to functioning motor prototypes. The unique soft switching and packaging approaches for the drive are being developed for implementation with silicon carbide electronics. Through collaboration with Georgia Tech Venture Lab, we have a strong focus on the commercialization of the technologies developed. Our enhanced thermal management concept delivers the fluid coolant into individual stator slots for evaporative heat removal. Specially designed micropillar array configurations aid two-phase flow by directing liquid and vapor movement through separate pathways. A 2 kilowatt motorette has been used for laboratory scale evaluation of the thermal performance of the embedded thermal management approach. We have developed a conceptual design for an integrated motor and drive incorporating our embedded evaporative cooling approach. A 25 kilowatt prototype of the motor unit with our thermal management approach is currently being fabricated by our vendor partner. We use a multi-physics simulation framework to design our integrated motor and drive to achieve a 3 times power density enhancement through the use of our unique technologies for stranded wound and hairpin wound motors. Compared to the single-phase water ethylene glycol cooled jacket design, our evaporative cooling approach allows for more than doubling of the current density while maintaining the maximum winding temperatures below 180 degrees C. We use volume of fluid-based computational fluid dynamics and heat transfer simulations to predict two-phase flow and temperature patterns through the coolant delivery path. Motor drives are a critical element of any electrical vehicle drivetrain. They perform the bidirectional DC to AC conversion required to drive the 3-phase motor used for propulsion from the DC battery. The industry standard is to use a 2-level pulse width modulation hard switching voltage source inverter for motor drive, yet well-known challenges limit the achievable power density and generate electromagnetic interference, common voltage, and reflected wave issues. These are getting worse when switching from conventional silicon technologies to newer, higher efficiency wide bandgap devices such as silicon carbide and limit the system level gain with these new power semiconductors. For these reasons, our team is proposing a new soft switching approach to realizing motor drives in electric vehicles with high power density, high efficiency, high operating temperature, benign failure modes, and controlled DVDT. It is felt that the proposed technology will help fully leverage the latest silicon carbide devices to bring significant improvements to the state of the art. We are currently developing a 25 kVA soft switching current source inverter prototype and a 60 kVA half bridge power card for demonstration. An integrated 60 kVA prototype will integrate the soft switching converter with the power module card and cold plate. The ultimate goal of the project is to integrate the inverter with custom packaging with the motor and carry out performance testing.